Hello, this is Mr. Jackson in Physics A. Today I want to talk about our new unit, which is going to be Chapter 3 in your book, but it's going to be in positive physics. It's going to be called acceleration. So we're going to talk about acceleration today. And I want to introduce you to some equations that we're going to need for this unit, okay? And so what I do, and this is something I learned in college, is I learned how to actually go through a chapter really quick and pull out all the mathematical equations first. But a great way to find those equations is if you go all the way to the end, right before the review, you always seem to find a study guide or a summary, and down in these summaries you tend to find all the equations that they have in this chapter. So I like to go right there and write those equations down. But before I do that, I want to introduce what acceleration really is, okay? So let's do that really quick, okay? Acceleration is different from constant velocity. We've already talked about constant velocity as when an object moves along, that object moves the same distance for every unit of time. So if a picture was taken, every picture would be the same distance apart. And we told you the equation for it in the last unit was average velocity is distance divided by time, okay? And so that is the way it's usually written, and that's what constant velocity is. But we're talking about now an object if it accelerates. And most objects do change speed sometime during their motion. So acceleration can be positive. The object can be speeding up and getting faster. Okay, and so here's an object, but here's an object that is decelerating. It was going faster, but then in the next unit of time it was going slower, then slower, then slower. So we can have an acceleration speeding up or a deceleration slowing down. So acceleration is simply defined as the rate at which an object changes velocity. Okay, and so that leads us basically to our first equation. Acceleration is equal to change in velocity over change in time. That's the basic definition of it. And so remember, we can always expand these things. Remember how when we wrote slope, we took these changes, and remember changes was subtraction. So we could say VF minus V0 over TF minus T0. And T0, our clock almost 99.999% of the time, all the time, starts at 0, okay? So I usually don't write this like this, but we're going to need this to be expanded like that, okay? And acceleration has unique units. Let's talk about the units really quick for acceleration. Acceleration is change in velocity over change in time. What does that mean? That means if you're going down the street and you're going in miles per hour, okay, then what happens is when you push on the gas pedal, you change your speed in a few seconds of time. So accelerations have two time units. And so you got to understand in a car, you change your miles per hour, in seconds of time. And so that would be the acceleration unit for a car, okay? But if we're doing something in physics and we talk about something going in meters per second and we're changing in seconds of time, if the two units are the same, physics likes to bring them together and write meters per second squared. But I want you to know it really means meters per second, right here, changing per second. And so this would still be an acceleration unit. It just looks weird, but that's what a car acceleration would be in the real world. This would be a marble down the incline if we were measuring in meters per second motion. So if the units are the same, they'll square them. So anytime you see a squared time unit, it is an acceleration number. Okay? So if you have 5 meters per second squared, it's an acceleration number. So what does that mean? Let's say that this marble is an acceleration of 1 meter per second squared. That means if the speed was 0 here, 1 second later, it is now going 1 meter per second, okay, in speed. And then at this place, it has gone up another 1 meter per second, so it's going 2 meters per second in speed. And then in the third unit of time, it's going 3 meters per second. And then in the fourth unit, now at this speed right here, it's going 4 meters per second. So its rate of increase is 1 meter per second every second. If this was a 2, then it would be 2, 4, 6, 8. That just means that's the change in the meter per second every second of time. Okay? That's what acceleration is talking about. It's talking about how the speed is increasing. Okay? So I want to develop these 4 equations, and you're going to need these. So please make sure you write these down. If you have an index card, put them on an index card or your cheat sheet so you have them by them all times. Okay? I'm going to rewrite this equation, and I'm going to put the A. So our equation number 1 is A equals VF minus VI all divided by T. I'm not going to write this T as a delta T anymore because it always starts, so the time you're given is just all you need, okay? That's the first and foremost equation we're going to use. That aligns with the one that they had at the end of this chapter. And so we're going to use that. Here it is right here. We're just going to make the bottom to be a T. Okay? So I want to take and show you the other 3 equations here. And so our second equation that we're going to want to always keep on hand, and these are very important equations, is we're going to keep this one right here, and x is distance, okay? And this is distance at 0 time, but since things start at a 0 distance, your starting point, we don't need this d, okay? And so I'm just going to rewrite this as x equals, and I'm going to get rid of the first x because it's just a 0 number, equals v 0, and I apologize, we've been using zeros in positive physics, so initial speed is a 0, okay? And so we're going to eat times time, okay, equal plus 1/2 a times time squared. So that's our second formula, okay? And then our third formula that's very important is VF squared equals VI, or V0 squared, plus 2 times A, which is your acceleration. And then it has a subtraction of the 2 distances, and if your first distance is the starting point, it just falls away. It's a 0. So I'm just going to call it a x for distance. We don't need to have 2 numbers. So when they do this in college books, and this is not a college book, it's a high school book, they end up giving you a whole bunch of extra symbols, and you need to get better. So I'm trying to help you guys make this simpler. So this is a simple equation. There is one more equation that is mentioned in the book, and it has to deal with talking about when a graph is used. And whenever you have a graph, I want to point this out, whenever you have a graph, and if you have velocity per time and a graph, as you accelerate, your velocity can increase. So we go from one speed to a new speed. Okay? So this might be 0 meters per second, and this could be 10 meters per second. And as you increase speed, and then maybe you stay at the same speed for a while, you don't change speed, now you've accelerated on the highway and you're there. Okay? If you want to find the distance that you traveled in this first chunk of time, okay, then they've discovered you just need to find the distance by finding the area under this shape. Well, what's the shape? It's a triangle. And a triangle, the area of a triangle is 1/2 base times height. Okay? So all we've got to do is go x is our distance equals 1/2. Our base is time. There it is. Times, and then this, adding our 2 speeds right here, is height. So a final equation which I want to add to our list, which is a very important equation, number 4, distance is equal to 1/2 VF plus V0 times time. Okay? So these are the equations that we're using. And I want you to understand why these are so important is They help us figure out what's the best one to use during a problem in this unit. And how I use them is I look for the missing information. Okay? We know that each one of these equations has something missing. Okay? And what's missing is one of our units, either distance, acceleration, final speed, or initial speed, or time. If you look in this equation, there is no x. So distance is missing. Okay? And here we have distance, we have initial speed, we have acceleration time, we have no final speed. Or velocity. Okay? VF. And in this one, you look here, we see there's no time units. So time is missing. And then in this one, we see that there is no letter A, like in all the rest. So acceleration information is missing. And so when we do a problem, and I'll show you in the future, when we do a problem, if one information is not given at all, then we want to find an equation that doesn't have that information. So we pick that equation, and it helps us solve for the other parts. Okay? So I want you to make sure you have this somewhere at all times. You need to know what acceleration is. You need to know a constant velocity. And if there's a change in speed, you cannot use this equation. You can only use these equations. So what I'm saying is this. When you do an acceleration problem, and let's say they ask you for acceleration, you solve for it, then they go and ask for distance, you can't sneak up here and try to use a v and a t from down here and then use this equation and solve for distance. You must use one of these equations that have distance in it. You can't mix these two equations. If you're going at constant speed, you only use this equation. If you're going and you're accelerating and changing speed, you can only use these four equations to solve the math from beginning to end. Okay? So, in the next video, I want to actually do some problems with you, but for right now, that's the basic idea about acceleration and the mathematics of acceleration. Okay? So make sure you have this written down. Make sure you have these notes somewhere that you can see them at all times. Blessings.